camera var. So, today is lecture 5. And today lecture would contain certain hard material. So I would tell it, but I could not expect that you will understand it just from the lecture, yes, basically. And because of this, the next class, I already going to open some system, either IBM, Google, or quantum circuit, and demonstrate, how you can, write those gates and show. But yes, I very, very encourage, yes, you to try, to do something yourself. Yes, at least register. Yes, and I mean, usually the user interface there is intuitive. Yes, so to create something and execute it, you can, by yourself. Yes, it doesn't need a lecture. Yes, but I strongly encourage. Yes, and please write in the chat if you did this or if you try to do but not successful, so I better understand what is your status in this direction. So, oops. So, I forgot to fix the QR code, but okay. So, short review of what has happened on the previous lecture. Yes. So first, I introduced the bracket notation. Yes. So the special way to write scalar products of quantum states, which I write in the form the quantum state and conjugacy to state, and they're thinking about this as a column. Yes, then conjugacy is a row. Yes, the product is number. But I also write this in such form that the bracket, the form of qubit, but in opposite direction. Yes, and you can do this for one qubit, you can do this for multi-qubit. This is just a notation. Yes, it would be just useful later when we do some computations, prove some statements. Yes. Yes. So here I use the formalism. Yes. So if the vector was originally just a k, when I write it in such form, yes, the coefficients become conjugated. But when I make a product of them, yes, no additional conjugation appears, and I just open a bracket and use a formalism. This k times j is equal to 1 if k equal to j, and 0 if k is not equal to j. Yes, you can use just this formalism, yes? And this is more or less idea that j forms orthonormal basis, k forms orthonormal basis, do they coincide? So this is idea of scalar product between them. But I make conjugacy on the moment when I translate a vector with error to the right to the vector with error to the left. Yeah, so I do conjugacy at the moment when I column make a row. The second thing which we did, we had discussed in a general form one qubit gates. And we introduced several special gates like NOT, Adamar, the Pauli gates, identity XYZ. But what is more important, I also introduced 4 special gates. There were rotations. Yeah, so I would not write their formulas now because they're formulas. Yes, but the general idea that this is certain basic matrices which has a special structure, And they really could be considered as a rotations in a two-dimensional complex linear space. But rotations over what? Yes, it's a question. Yes, so in particular, they have a rotation idea, so that if you rotate to the alpha, and after this rotate to the beta, then you rotate to alpha plus beta. Yes, so this is the rotation property. And I not showed, I just postulated the fact that any one qubit gate can be represented in such form. So 3 rotations, yes, and after this phase change of the gate. So I postulated it. I didn't prove it, yes, but the general philosophy that, okay, assume that those guys are implemented, then any one qubit gate can be implemented. So this is why we usually don't bother ourselves with how to implement one qubit gate. Yes. So we considered several special. We go to 2 qubit gates. Their space of 2 qubit gates is much richer. So I started with a special controlled NOT gate, yes, which is denoted here, and acts on a basis vectors as the following. Yes, so that doesn't touch the first one. So on one where there is a black dot, and on the second one, if the first is 0, then it do nothing. But if the first is 1, then it apply not to the second one. Yes, so this is a logical operation. This is operator if. Yes, in terms of, but in quantum computer. Yes. After this, I consider the generalizations because you can do this not control NOT, but control U with a difference which operator you apply. Yes. And I also postulated the fact that any gate can be a composition of controlled NOT. So controlled NOT is enough, and rotations. Yes, but here I also showed some formulas. For example, assuming that U is presented in such form, I showed explicitly, yes, how to present controlled U via controlled NOT and such rotations. I also introduced some other special 2 qubit gates. There was controlled Z, which is another form of quantum oracle. I would discuss it in more details actually later when I would speak about Grover algorithm. So I introduced a swap operator which changed the 2 qubits, values of 2 qubits, yes. And it is a special operator because it is related to connectivity graph of quantum computer. Because in quantum computer, not all qubits are physically nearby. So even that logically you can apply, for example, control NOT to any 2 qubits, yes, but you physically can apply it only to those who are nearby. Yes, so and in that case, the implementation is that you do swap, yes, change it, apply and do swap back. Yes. So this was what has happened. So today I would first of all finish kind of 1-2 qubit story. And after this, I will go to really multiple qubit operations. So operations which contains n qubit. Yes. And this has 2 goals. First, to demonstrate how, quantum program can be more difficult than classical program. And another is just to show some tricks which we have to do. And okay, I also will introduce control U gate, which would be a part of general idea of programming. So before I come to multiple controls, I'm finishing with a small number of qubits. So why people use C naught, not other operators so much? And there is a reason for that. So let us see on a 2-qubit state. We know that it could be direct product state or it can be entangled. Yes. And let us measure if it's entangled a bit or entangled strongly. Yes. We remember that it is entangled, it is a direct product if and only if product BC and product AD are equal. Yes, so such expression is equal to 0. Yes, and let us just say that, okay, this would be the measure how much it is entangled. Yes, and we introduce a special entanglement, which would be a square root of this value. I don't know exactly why, but people put square root on it. And what I want now to do to understand which gates able to create a lot of entanglement and which gates are not really able to create entanglement. Yes. For example, if we apply 1-qubit gate, yes, so it is never create entanglement. Yes. Yes. Star is conjugacy. Yes. So sometimes I use bar, sometimes I use star. Yes. That's because yes, this is equivalent notation. Yeah, so if I apply 1-qubit state, 1-qubit gate, so then if I started with direct product, then I would end up with direct product. Yes. Is direct product state, yes. So we don't say independent, even that it is informally correct, yes. So if it is equal to 0, then it is a direct product state, yes. So then it is not entangled. And kind of more is this value, then we consider it as more entangled, yes. And remember that a squared plus b squared plus c squared plus d squared is equal to 1. Yes, so it has a limit. It cannot be infinity. Yes. Yes, for me, and also why I multiply by 2. Yes, so for me, I don't have a good answer to this question, but by some reason, I mean, all the textbooks existing in quantum computers do this. Yes. Because in the end, I put absolute value. Yes, I completely agree. But by some reason, all of them write like this, and I prefer not to overlap with classics. Yes. And moreover, why they multiplied by 2? Why, as a real kind of measure of entanglement, we make not the value by itself, but square root of this value. With respect to what? Okay, but you see, rescaling is forbidden. I am scaled by 1. Yes. Okay, yes, and now, but what I want to understand, how operator can create entanglement. And for this, I consider my operator and look on a direct product state and look on an image of this under operator. So what operator is doing with direct product states, yes? And then it would be certain value, yes, of entanglement of it. And I want to consider average over all direct product states. Yes, but in that case, I need to choose a measure via which I average. And this becomes a measure of a block sphere. Yes, so this is what particularly block sphere is needed, because we still want to remember which states are close to each other. Yes, and in that case, we consider the sphere, yes, and I mean, this is the expression, this becomes certain integral, yes, four-dimensional integral, and 4, because phi is a two-dimensional, phi1 is two-dimensional sphere, phi2 is two-dimensional sphere. Yes, so in total, this is a four-dimensional integral. Yes, the space of psi1 times psi2 is a four-dimensional real space. Yeah, so this becomes a four-dimensional integral. And all of you will tell, thanks to me, that I'm not going to show examples of calculation of this integral. On the next table, I just show the values. Yes, so people calculated it for us. Yes. So first of all, if you independently act on two qubits, then entangled power is 0. So you cannot, from entangled state, create not entangled state. C naught has 2/9, and 2/9 is the largest value and largest possible value among all the operators. Also, there are other operators which has the same property. Yes, this was ISWOF, which I introduced previous time. There is Berkeley gate. It is here. Yes, but it doesn't matter. Yes, as we discussed on previous lecture, actually all of them can be. There is a scheme which connects. Let's say Berkeley, you can write Berkeley via CNOT gate. You can write CNOT gate via Berkeley gate. Yes, so, but this explains why, if you go and read the physical implementation, yes, so sometimes physically implemented is not CNOT. Sometimes physically implemented is ISWAP, or physically implemented is Berkeley, yes? But they have certain preferences against, for example, square root of swap operator. Yes? So EP of U is always less or equal than 2/9. It's always less or equal than 2/9. So 2/9 is the largest possible value. Yes, so, but I mean, this is not obvious, yes, because you need to consider integral. Yes, it's not that the each value. So I think each value is less than 1. Yes, for this. Yes, the entanglement is necessary less than 1. Yes, so now here, so entanglement is of any vector is not more than 1. Yes, so yes, you can say that entanglement power is not more than 1, but it's not possible that whatever direct product you consider, you will get a state with a full entanglement. Yes, I think might be, actually, this is the reason why people put 2 here, just because the largest is 1/2 here, 1/2 here, and here is 1 over square root of 2, 1 over square root of 2, and this will give you value of entanglement 1. Yes, but the actual average is the greatest value is 2/9. But this is not a trivial statement, so this is, you have to integrate over a sphere and somehow look. No, I mean, you could look on a standard measure on a sphere. Yes, so sphere has not Lebesgue measure, but how it's called, Haar measure. Yes, on it. There is a standard measure on it. Yes, and, or you can write it in a polar coordinates phi psi, theta phi, yes, and say that this is a product. Yeah. But here I can see the average. If it is more than 1, I would just normalize. Yes, this is. Yes, and here this is a philosophical story which explains why, I mean, CNOT is also better. Yes, because it has maximum entanglement power which you can have. Yes, so CNOT is logically understandable. It has the largest entanglement power, so and you stay relaxed, everything will go with it. There is an interesting concept of universal gate. So here I showed two examples of them, yes. And where here there are certain parameters, theta, alpha, theta, phi, all of them are rationally independent, or rationally independent is pi, yes, together. And the idea is the following. So if you have implementation of this 3-qubit operator with one single value of theta, which is rationally independent, then it's possible to prove that any gate on any number of qubits can be approximated with any precision by a certain composition of those gates. Yes, so kind of theoretically, it's enough to implement it, and after this you can implement almost everything. Yes, but it doesn't tell you how long would be the program. Yes, and the same for this one. This is 2 qubit. Yes, so there is one 2-qubit gate which is enough to implement everything. Yes, but we will not use this concept. Yes, because of course with the time, so you need to have very long sequences of them, and in that case you need to have implementation of those operators with very high precision. Yes, and you cannot expect this. Yes, from the device. So from now on, the course a bit loses his how to say that it is go like forward. Yes, now it becomes a tree-like, start to have tree-like structure. Yes, so I cannot say next topic is just after previous, so they start to have some relations. So now I would like to say how to implement everything which is possible on classical computer, how I can implement it on quantum computer. But I cannot say this now. For this, I need to develop a bit more what we can do in quantum computers. Yes, so let me do this little step. Yes. So this is so-called controlled U gate. Yes, it's the same as controlled gate, but with 2 controlling qubits. So it never changes the value of 2 controlling qubits. And if both of them are equal to 1, then I apply U to the third qubit. And if at least of them is 0, I don't do anything. Yeah, so like this. Yeah, so 0, 0, 5 will go to 0, 0, 5, 0, 1, 5 go to 0, 1, 5, 1, 0, 5 go to 1, 0, 5, but 1, 1, 5 goes to 1 by U5. Yes, and I defined it not on all vectors, yes, but by linearity, I can consider, I can define it on the whole, on any 3 qubit states. Yes, and the special case of this is when U is equal to naught. So controlled naught operator. Let me draw it. Yes, controlled naught. So I draw it in the same style as I was drawing controlled naught. The feature is that this operator is equivalent to some operator which is very important in classical computations. And this is controlled XOR operator. Yeah, so it's equal. So if I write classical operator now in the notation of quantum bits, so I put here XOR. Yes. And the XOR acts like this. So 0, 0 goes to 0, 0. 0, 1 goes to 0, 1. 1, 0 goes to 1, 1. And 1, 1 goes to 1, 0. So it puts here, yes, it puts here the value 1 if only one of them is equal to 1. Yes, this is in Russian исключающее или, I don't know how to translate it to English, to XOR, yes, so, but XOR. Yeah, so this is controlled XOR becomes. And the controlled XOR plays important role in classical computation. And just operator controlled not, yes, it's quantum analog. Yes, of which, but we need to understand how we can implement controlled not. First of all, if you go to certain systems like IBM quantum system, you will see direct implementation of controlled not. So you don't need to implement it yourself. Yes, so it's included into the system. But still, okay, so before I show how to do this, I will say why it is so important. Yeah, so how I assume that we know how to implement controlled not. This is a pre-assumption. Yes, I will show this how to do this, but if we can do this, then any classical algorithm in a certain way can be implemented on quantum computer. And here I would make two postulates from the theory of classical computation. I will not prove them, so I suggest you to believe me. Postulate 1. So if we have classical reversible computation, yes, then it can be implemented only using controlled XOR. Yes, only using this very special operation. Because, I mean, it's reversible, and I mean, people were smart enough and proved that it's a mathematical or computer science theorem. Yes? And postulate 2, that any classical computation on n bits can be made reversible if you have n ancilla bits. Yeah, so if you have your system where you do your calculation, here you allow yourself and or whatever non-reversible, then you can, and here was n bits, you can add n more bits, modify your program somehow, and and it would calculate the same output on n bits, but would be reversible, taking into account those. Yes. What? Why I call it postulate, not a theorem? Yes. Because I don't know how to formulate. I'm not from computer science, and you know that's you need to formulate this theorem. You need to tell what is an algorithm. Yes, algorithm is a sequence of operations of such type, and you need to take very carefully the lengths of this, the lengths of the program, basically. So for this, you need to define all of this. So I would like to use the term theorem, yes, when I really have a mathematical formulation, yes. And here I still leave it on hand waving, yes.
Sergey.
Yes.
So I guess this kind of makes sense if you consider those extra bits are basically just to like retain the original information, right? So you can return.
Yes. Basically, yes.
Okay, yeah, I see.
So kind of like informally speaking, yes, when you apply AND operator, you lose a bit information, yes, but you can store it in ancilla qubits. This is very informal, yes, because you theoretically can have more end operations than were number of bits, yes? But the feature is that your number of ancilla bits is not the number of operators which you did here. It's the same as number of bits which you did here. Yes, and this is not my theorem. Yes, this is theory of computer science of classical computations. Yes, so I don't want to touch it very deeply. Yes, so I just want, for me, as a consequence of this, remember that if I have certain classical algorithm and bits, then I can consider a quantum computer with 2n qubits and a program which do then and able to create a program which do the same as was done by a classical program. Yes, and because combining those two postulates, the most important gate is 6 XOR. Yes, so the most important gate here is control not. Yes, which is just equivalent to equal to 6 XOR. Yes, so kind of any classical algorithm can be decomposed into combination of control not. And this is a statement up to now. Yes. Later we will see how easily or difficult to do this. We will see that summation operation can be done relatively, classical summation can be done relatively easy, and like multiplication I would not try to do, yes, but I would always assume that we can do this. So there is a certain operation which do multiplication, yes, because it exists in classical computers, so it exists in quantum computers, but might be not very convenient. Yeah, so this is, so I started with the fact that this is a curse, reversibility, yes, that we cannot, because of this, yes, we cannot implement everything, but with the idea of extra qubits, we can. But remember that multiplying number of qubits by 2 is currently a huge problem, yes, because we are not speaking about gigabytes, yes, now we speak about 100 qubits, yes, so if you multiply by 2, so then we reduced 100 to 50, yes, so which is a reduction, significant reduction. Yes, so before I go to like concrete schemes, a boring part, but I mean, what is quantum circuit? And quantum circuit is a picture like this. Yes, so it's I have a qubits with corresponding lines to them. I put on them gates. This is a notation. Yes, so how I do this? So it could be 1 qubit gate. It can be multiple qubit gates. It can be controlled gate. It can be multiple control gate. It can be multiple control where one of the control is 1 and one of the control is 0, and I mean, etc., etc., etc. Yes. So recall that this is notation for I swap. This is notation for swap. This becomes a notation for controlled swap. Yes. So that if this bit is 0, then I do nothing with those. If this bit is 1, then those two are changing. Yes. So this is the story. And typical things, we need to speak about complexity of algorithms. Yes. And here would be important properties. Width, it is number of qubits. So here it is 4. Size, it's a number of gates in total. So 1, 2, 3, 4, 5, 6, 7, 8, and I would not continue. And length is the number of qubits which cannot be done parallel. Yes. So general idea, so you can move the gate along the strings unless it intersects something. Yes. So it doesn't matter what I do first, H or X. Yes, because they are at the same time. But I cannot move this controlled node, put it between rotations and C, because to do this I need to cross that. Yes, and the length is the how much it can be up to parallelization. So here it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, measurement I do not. Yes. And another thing which we will see and which is a really important metric, but for say current state of quantum computers, I believe that at some moment it becomes less important metric, is that when you write such a scheme and execute it on a real quantum computer, so in the end it would be decomposed into 1 qubit gates and C naught. Yeah, so that this complicated operator would be represented somehow as a 1 qubit gates and C naught. And the question is how many C naught operators you would have in this representation. Because C naught operators up to now are not of very good quality, and so because of this, it takes certain, you try to minimize them. The program can have bigger length or bigger size, but it has less C naught operators, it is still better. And if when you construct a scheme, you should try to minimize number of C naught operators, not number of gates as it is. Yes, and some notational remarks. Yes, because there would be usual situation that I draw scheme like on the previous slide, but we will make calculations in states. Yes, for the states, we would not just do calculations on a scheme as it is. And so that we need some rules how to convert one to another. Yes, if we have two consequent gates, so this is just their multiplication. Yes, but we apply from the left to the right. So we first multiply by u1 and second we multiply by u2. So if we have one qubit on which there is no operation and on other there is some operation, that this is identity tensor U. If we have two parallel operators A and B, then this is the same as their tensor product. And so this is a notational remark. Now let me come to examples which at the same time would be important for future. Let us consider controlled U operator, and let us try to represent it as a composition of two qubit operations. And here is the scheme which do this. Yes, and here there is a vector V, there is operator V, and it's not arbitrary operator, it's such operator that its square is equal to U. Yes, so square root of U. So how we can check that those two schemes are equivalent? Yes, so we need to check this on a, we should choose ourselves what the basis states we consider. Yes, and so here I suggest to consider those four basis states. Yes, and let us make together the calculation. So why these two schemes are equivalent? So I say that they are equivalent. And, but of course, you can trust me, but then we not, add more in understanding of the world of quantum computers. Yes, and moreover, there will be too many things which I would ask to remember in that case. What? V transpose or V inverse, yes, it's the same because V is unitary operator. So this is inverse or transpose of it. Yes, it's the same. Transpose and conjugate, yes. Transpose and conjugate. It's inverse. So let us see. So by the first scheme, 0, 0, 5 will go to where? And by definition of control, control Q. It goes to 0, 0, 5. But now let us go to the second, yes, implementation. So here we have 5, 1, 2, 3, 4, 5 operations. Yes. What? Let me the first do me. Yes. So 1, 2, 3, 4, 5. Yes. So what will do control V? Nothing. Yes, because control is 0. Yes. So it would here it actually more convenient to write it at the 3 qubits. Yes. What will do the second? Nothing, nothing, and nothing. Yes. None of the control operators will act. Yes. Yes. So okay, then they are equivalent. Those two operations. Okay, let us now go to a more tricky story. Yes, let us go to 0, 1, 5. Yes. So what will do the first? Nothing. But now that's a question, what will do the second? Who would like to try his or speak to me at least? Zero. Oh, those who are in Zoom, can you see the calculations on the board?
Yes, so it's cut off a bit to the right, but yeah.
Okay, yeah. Yes. Do you see the line where I do you see the line 1 where I point? No.
I only
The
see
line
lines 2 and 3.
2 and 3. Okay.
Okay. Sorry. Yeah. So when we're computing the first node, it's controlled by this value, right? And in our case, it's 1. So therefore, my operator acts here. V acts on phi, right? Now, the next thing is controlled by the value of the first one, which is 0. So nothing changes. Now, we apply the inverse operator, because it is controlled by 1. Let me maybe underline what is a controlling node. In this case, this is a controlling one. In this case, this is a controlling one. In this case, this is a controlling one. So I act, and I act back. So, okay, maybe let me spell it out, that this is this fancy transposition operation, V transposed V, applied to phi. And now I should move to the next stage. And of course, these two cancel out, again, because of unitarity, so vanish. And then the two operations are controlled by the first node, which is 0. Therefore, nothing changes. So basically, this is the final answer. 0, 1, phi. As Sergey predicted for us, that nothing changes.
Thank you, Altan. So let's do the next. Let's just we never push people to go. But I push you to speak to me. Yes. So I will write. Yes. So first of all, 0, 1, 5 by control U will go to 0, 1, 5. Yes. So nothing is changed. Yes. How now will operate 0, 1, 5 in this scheme? Yes. So first we have a controlled V. Yes. Which qubit is controlling? Yes. So it is 0. So nothing is changing. Yes. Second thing, we have a controlled node with controlling first qubit. So it would really change something. Yes. So it goes to 1, 1, 5. Yes. Now we applied control V inverse. Yes. And with the second qubit controlling. Yes. So it will go to 1, 1, V inverse phi. Yes. So after this, we once again apply control node. Yes, with this acting. So it will go to 1, 0, V minus 1 phi. Yes. And the last controlled V, controlled by this. So this would go to 1, 0, V minus 1 phi. Yes, and this goes out. Yes, so this the same as control U. So now only the last thing we need to check, yes, is this case when both of them are 1, 1. Yes. Yes. Let us first make a just straightforward calculation, and after this, let's try to see, why it is correct, not with all the calculations which were done here. Yes, let us see how it acts. Yes, it acts 1, 1, phi goes this controlled V. It goes to 1, 1, V phi. Controlled node, yes, applying the first one makes it 1, 0, V phi. After this, we are controlling by second qubit, so do nothing. After this, we do once again controlled node. Do once again controlled node. So 1, 1, V phi, and do this the second time. Yes, 1, 1, V phi. And so this is exactly equal to 1 u phi. So exactly what we wanted to get. Yes, so this is a straightforward calculation. So if you want to make it not so straightforward, but more using brains and less using heads, how it can be achieved. So first of all, let us look on the first two qubits. Like the first qubit would never change because there is no single gate which can change it. The second qubit. So those three operations doesn't change it. And the other two operations is 2 times applied control not. They either both time apply not or both time do nothing. Yes, so the state of this qubit in the end is the same. So appears now a question, what is happening with the third one? Yes, first of all, the general idea was that this was what I was doing. Yes, I was just to making, okay, there are 4 cases. Let me find the proper controlled V or V minus 1 in such way that in 3 cases I will get nothing applied in the end. So V and V minus 1 applied the same number of times. And in the case of 1, 1, we applied 2 times V. So this was my goal. Yes, and another thing we can just look. Yes, so kind of it's 0, 0. So then just nothing ever executed. If 0, 1, yes, then executed this one and this one. Yes, because if this, so assume that the first one is 0, then this doesn't work, this doesn't work, and this doesn't work. And so the rest, what is happening is controlled V and controlled V minus 1. Yes, so this would be nothing. Yes, and if the first one is 1, okay, then we need to check. Yes, so kind of the way just to write everything for basis states is longer. Yes, but you have less chances to make mistake. If you do some logical consideration, then you need to write less, but you can make mistakes. Yes, so that's logical mistakes. So here I do not have a recommendation what is more good for you. Yes, so I personally, for the cases when I'm sure, prefer logical considerations. But as soon as I have any doubt, I go to as direct calculations as possible. This is for myself. Okay. Some remarks. Yes. So first of all, we never were using that U acts on a 1 qubit. It can be acting on multiple qubits as well. Yes. So that's U is not necessarily 1 qubit operation. It could be multiple qubit operation. The second thing is that how to calculate square root of operator, I didn't tell as before. But there are 2 important cases when it is clear how to do. The first case is if U was a rotation, then square root of rotation is a rotation on a half angle. And so that's easy example. And the second thing corresponds to the case when it is really on multi-qubits. So assuming that U was controlled something, yes, then its square root is controlled square root of this something. If U was controlled W, then square root of U is controlled V 1/2. You can put minus or you can not put minus. Controlled, not minus, it's controlled W. This would be used as a notation for so we have controlled U gate. So let us do a notational remark. Yes. So if we draw on a scheme, on a string notation, then controlled V looks like this. If we write it on a line, yes, then we write it C, which means control, not minus, but tire. So how tire is translated? A line, yes, defiz W. So this is not minus. This is notation for controlled not controlled W. So I'm not sure longer or shorter it is. Yes, controlled W. And of course, you always, if it is not obvious from the situation, you will need to write which qubit this is acting. Yes, for example, in this particular case, this is 1, 2. Yes. So, but usually I would omit this indexes because usually it's clear from the context how it is happening. Yes, and in that case, if I do controlled V to the power 1/2, controlled V to the power 1/2, then it would be controlled V. Yeah, so this is together. So there are two particular cases how I can find the square root. In particular, this means that if I would like to consider controlled U, so consider the situation when I have k qubits which controls the execution of U. Yes, K, here it is K. Then I could consider this as a sequence of diagrams. Yes, I will start it like I have controlled in the special operator, which is has a lot of things, yes, and this would be just controlled U. And if here there was K of controls, here it would be K minus 2 controls. Yes, I can consider square root of this operator, yes, and substitute it into this scheme. Yes, and in that case, I will find a representation of K control U via K minus 1 control U. Yeah, so V would be equal to K minus 2 U. Yes, and because here we see controlled V, so it becomes K minus 1 control. Yeah, so we reduce number of controls by 1. Yes, and we can continue this procedure unless we get. Yes, yeah. So now my question. So I have a controlled U. Yes, 10 controls, 10 qubits controls execution of 1, like hypothetical situation. And I want to construct a scheme which would make only operations on 2 qubits and implement this long operator. I'm telling the following, okay, so assume that here there are K controls. I would put, instead of U, So k minus 2 controls u. So this would be multiple qubit operation. Yes? What might be? Yes. 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 So let me tell the following. Actually, kind of soon we will have a break. Yes, 5 minutes break, and most of the lecture after the break, yes, would be constructing of good implementation of this operator. Now I speak how we can create bad implementation of this operator. Yes, so theoretically, yes, you can consider this. Substitute here instead of u. So assume that here is a 10 controls. Yes, 10 controls operator. We instead of u, we substitute 8 times control u. Yes, and so this becomes 9 qubits here. Yes, and in that case, still this scheme is correct. Yes, but inside the scheme there would be those control nodes, and there would be control v. So it would be 9 control operator, 9 controls v. Yes, and this is we reduce 10 to 9. We can reduce 9 to 8, 8 to 7, and so on. And the problem is that we all these substituted to each other. Yeah? So because here there was 1 control operator, here there are 3 control operators. So each time the number of these controls will triples. Yes, and then it would be exponentially long. So then what's the point? Yes, we want to use quantum computers to have something not exponentially long. And the second thing is exactly what Altan told, that at some moment we would need to construct u to the power 1 over 2k minus 1. I mean, this is, assume that even it is a rotation, yes, then this should be a rotation for the angle alpha divided by 2 to the power 9. And how precise should be our physical system to be able to make such a really small rotation? Yes, so that's too much to system. Yes, so that's, this way is not very good. This is a theoretical, very good solution for everything, but there are a lot of questions. Okay, so now I would come to how to say more systematic studies of n-qubit operations. Yes, but let's first have 5 minutes break. Just a second, I will press pauza. Gravasao. Yes, great. So question. Mm-hmm. So I think I understand. I'm not sure. I will try to answer. Yes, and with the answer, we will see did I correctly understand it. So can you do the following? Yes, basically. So if you have 0, 5, yes, you have A phi, yes, which do the following. So A goes to A, and if A equal to 0, then phi goes to U1, U0, phi, And if A is equal to 1, phi goes to A is equal to 1, goes to U1 phi. Is it your statement, more or less? No. Okay. Then, okay. First of all, this, yes, it's possible to implement, yes, because you first do controlled by 0, U0, yes, and after this you do controlled by 1, U1, yes. Starts into a second question, which you know. You see, if I already know that this is happening, then I already know what would happen for this state, for such state. Yes, because the first qubits never changes. Yes, but it will go to 1 over square root of 2, 0, U0, phi, plus 1 over square root of 2, 1, U1 phi. Yes? So if you set it up what it is do for 0 and 1, you set it up what it is doing for half sum of 0 and 1. Yes? And okay, theoretically, you can choose here not values 0 and 1. You can choose two orthonormal states here, arbitrary, yes, and change the thing, yes. Usually, yes, we not introduce special type of these operations, yes. We just use so yes, you just do that the following construction. So you put here this your favorite controlled U, and here you put operator A, which properly transforms the basis. And after this, you put here A minus 1. Yes, just to move it back, the basis. Yes, so if you put your basis to 0, 1, you apply control operator, you return back the basis. Yes, so typically it's done a story like this. And yes, so this is a problematic part of what I'm doing, yes, because if I would describe all the basic operations, yes, and this what Altan asked is also kind of a basic operation, then I would spend all the course in this, yes, but I still want, you know, to do step by step, but at some moment reach a high level quantum programming. Yes, it still would be on the pictures like with bits, yes, but it could be high level. I would like to introduce a complicated basic blocks and start to build program from complicated basic blocks. Yes, so that the course would consist of such parts. And one of the important basic blocks is just multiple controlled operator. Yes, okay, let me consider a few more. Things. So just to practice, yes, it's intuitively it seems that we have not much to do. So let us consider certain permutations of the basis. Yes. So if you have the basis state G1, G2, Gn, it reverses, kind of it changes the qubits, and this is how looks matrix is the orange is 1, the white is 0. Yes, and so this looks like this. Yes, which scheme can implement this? Yeah, so that we should just change the first and the last, and second with the pre-last, and so on. Yes, we should make swaps. Yes. And here there is a detail, yes, because if we can really swap any two of them, yes, then I will use n divided by n over 2 operations. Yes. Or n minus 1 of yes, operations. But there is a connectivity graph underlying. Yes, so you cannot swap any two qubits with single operation. You can swap only neighbor. And connectivity graph is a complicated concept. Assume that the connected are neighbor bits. Yes. Then how it would look like? Yes. Okay, here I showed how it would look like for 4 qubits. Yes. Then the scheme becomes actually much more complicated. Yes. Yes. So check. Yes. So kind of let us see where this one goes. Yes. So this first goes to second, second goes to third, third goes to fourth, and it's on the place. Yes. What do the second? It goes to the first. From first go to second. From second go to third. What is doing third? It goes to fourth, third, second. And fourth go to third, second, first. Yes, I mean, this is the philosophical scheme. I don't want us to spend super much time on constructing such sequences of swaps. Yes. So actually for 6, it is here. And, this is for 5. Okay, this is for 5. But in general, the idea is that number of operations which I would have here, yes, is approximately would be of order n squared. Yes, it would be n squared over 2, very roughly speaking. And this means that the fact that we have connectivity graph, yes, can change even such simple algorithm from n divided by 2 to n squared divided by 2. Yes, so connectivity graph is something which we cannot ignore in such kind of stories. Yes? So this is sad news. So the second, yes, is when we just roll. Yes, G1, G2, Gn goes to G2, G3, Gn, and I forgot to write G1. Here, so here's G1. Yes, so. Yes, this is just usual permutation, but on quantum bits. Yes, so that's, but yes, this is just usual permutation. What? Might be, yes, might be. We change the first, second, second, first. So here the scheme is trivial. But now let me come to real quantum computation. So if Altan insists, yes. So because this was, everything was warmed up to this question. Yes, actually. And let us consider permutation, which will move a number k, the basis states k, to basis state k plus 1. Yes, so here is the matrix, yes, corresponding to it. And it's not so easy to implement this one because you cannot just swap the bits, yes, because you kind of, what is happening? Yes, assume that you have 1, 2, 3, 4, 5, yes. What? It's addition, it's plus 1. And now we will see that plus 1 is far from trivial operation here. How to say, it's true and not true at the same time, yes? Because in usual bits, you have, like how you do usually, by yourself. how you do +1. Yes, you add to the last digit. Remember, should you have how to say, +1 to the next? Yes, and so on. Yes, you use this as a memory, which you each time erase. You don't have such a luxury in quantum computers. Because it's, yes, the way how you usually compute +1 is not reversible way. Yes, even that operation +1 is reversible. Yes, of course, +1 is a reversible operation, so it could be implemented in terms of controlled XOR, as I made in postulate 1. Yes, so that's possible. But let me come in a more detail. Yes, so then I need to implement +1. Yes, here. And I just make a certain permutation of bits, first and last, change the order. Yes, and in that case, actually, this is a certain combination of multiple control nodes. Yes, so P was the one which first is the last is the first. Yes. Yes, and in that case, how you do this? Yes, you, how to say, when you change the first, yes, when all the previous were 1, yes, control, no. When you change the second, if all the previous were 1, and so on. Yes, so this is how easy summation works. So this is a reversible scheme for +1. Yes, and I put permutation just to use the classic, the way how I use it, that control is on top and controllable is on bottom. Yeah, so how you add +1? Yeah, so if you have a certain number, 0, 1, 1, 0, 1, 1, yes, when, if you make +1, yes, when this should become 1? Only if all previous is 1. Yes, okay, so in that case, it is still 0. When this 1, so it was 1, when it should become 0? When all previous were 1. Yes, so this is still 1. So this is 1. Now, okay, when this should becomes, when this should changes? When all previous were 1. Yes, so it changes. And in that case, this one also needs to be changed, and this one also needs to be changed. Yes, and so this is exactly the scheme which I showed here. But there is a problem with this scheme, that I need to have a good implementation of controlled node. Yes, how I can create it. Yes, that's a feature, and actually kind of most of the lecture, okay, not only today, but part of the next lecture would be devoted to effective ways how to construct such type of things. Yes. So how I can add +1, how I can construct control. So before I do this, I would like to say that in case, yes, and this is exactly to what is referring Altan, yes, in case if we have as many ancilla qubits as we want, how we can implement +1 easily, yes? In that case, we just state that we have this Q1, Q2, Q3, Q4, Q5, our quantum bits. And we have R2, R3, R4, R5, our ancilla bits, which we put in the memory. And we just do the following. So kind of, okay, Q1, it's we will add the +1, yes, to Q1 always. Just, and we calculate two things. We have an input, what we add to it, and we should understand, we have what we had, what we are adding, what value we have, and then output. We get the value which is new value and what we should add to the next column. Yes, basically. So the idea is the following. Yes. So yes, we have a Q5, Q4, Q3, Q2, Q1. We want to write +1. Yes, here. We do the following. We need to have value Q1 plus 1 here. And we need to understand we should add to the next term 0 or 1. Yes? And let us just, construct such a construction which would, so this was something. So here was 0, Q1, 1, yes? And it will go, yes, to what? It will go to this value, yes, which we should add to the next one, yes, Q1 plus 1, and this one would be lost. Yes, basically. We don't care what is here. And we can construct such a reversible operation. I actually showed it here. Yes, so it's operation like this. And in that case, we can start to apply this operation, one by one. Yes, +1. So we start with +1. After this, calculated this value, calculated Q2 plus this value, and so on. Yes, so if we have in a classical computer, if we have extra memory, yes, then we can calculate it number by number. Yes, with very easy operation. I feel that I feel that the audience got lost. Yes. So what I'm trying to say. Yes, I'm trying to say that if we have a lot of ancilla qubits, then operation +1 is very easy because we kind of can summate Stolbic, summate arithmetically. Yes. So we can summate in the following form. Yes, let me summate is the same idea. Yes, as here. This number +1. Yes, what is the answer? I write here 0 and I write here 1. Yes, because I need to add 1. So now I summate those two. I get 0 and write here 1. So let me, So let me first see how it works here. And after this, I will, show the mapping of one to another. Yes? After this, I do this 1 plus 0 is 1, but here I should put 0. Yes, 0 plus 1 is 1, but here I should put 0. 0 plus 1 is 1, and here I should put 0. I put 0 here, and it's not necessary to remember what to do next. And this is the idea exactly. So look on this operation now. This is, let me see, this is Q1, Q2, Q3, Q4, and Q5. Yes, as written here. Okay, here this is, I think, for 4. No, 4. Yeah, this is for 4. Yes, so let me do like this. Yes, so assume that I have 4 numbers. Yes, then this first, just a second. I need to find an analogy. Just a second. Q4 is the first digit of the number. No, because in that case, +1 to it is not implemented. But I have not here, which is the only one which exists. Just a second, I need to. Let me see. Well, it's very strange because I should do first a 3-qubit operation. Yeah? So that should be. Ah, okay. I see. No, this is Q0, Q1, Q2, Q3. Yes, so this is not Q1, Q2, Q3, Q4. This is Q0, Q1, Q2, Q3. And I'm adding +1. Yes? So what should be here as an output? Yes, there should be not of Q0. Yes, not of Q0. This is this guy. What should be here? It should be like assume that Q4, Q5, Q6, Q7 originally are zeros. And this would be Q4, Q5, Q6, Q7. Here, it's like this. Yes? So Q4, so the number which I should put here, yes, is exactly controlled Q0. So if Q0 was 1, it should become 1. Yes? So this is, so here I calculated Q4 and calculated new value of Q0. Yes? So the next step, I calculate when Q5 should be 1. When Q5 should be 1. When Q4 and Q1 are 1. This is the only story, yes? So this guy calculates Q5. Yes, and after this, I need to find what is the value of Q1 plus Q4. And this is controlled not to Q1. If Q4 is 1, I should change Q1. If Q4 is 0, I should not change Q1. Yes? And so, and by such blocks, yes, I continue. Yes? But this is an assumption that I have as many ancilla qubits, yes, as I want. And this is what Altan is referring to. Yes, that okay, for why we do this? Because in classical computer, you will do like this, yes, basically. And the same story we can easily do in quantum computer as well. Yes, but I want to calculate, I mean, all of this, you know, with small time and with small number of ancilla qubits. This is what I want. Yes, I told that we already considered this idea, which would create us exponential scheme. Yes, I want to find other idea for control node. And the idea is the following. Now for Altan is potentially time to wake up. Yes, to join. Yes, back. Because assume that we have a lot of controls and not. Yes, and we have just one ancilla qubit, but we know that this ancilla qubit is 0 in the initial state. Then we can break this into 2 parts. Yes, and first calculate control to this guy. And after this, the rest controlled with the last one. So those schemes are equivalent. Yes, because, okay, the first number of qubits doesn't change. Yes, and this one would be executed only if all of these are one, and this guy is one only if all those are one. Yes, so this schema equivalent. I mean, what means equivalent? Yes, the problem that they're not exactly equivalent because this intermediate, this ancilla qubit, potentially will change. Yes, and this is one thing. And another thing that we assumed that it was in zero state. Yes, so it cannot be reusable or it cannot be taken from somewhere else. And there is a trick which calls uncompute trick, yes, and which allows us to repeat the same idea, yes, but without assumption that initial qubit was zero, yes, and we will do like the scheme would work independently for what was the input or what was the value of this ancilla qubit, and moreover, it would not change in the end. So uncompute trick. So the first two parts is the same as here. And after this, I repeat it once again. Yes. And here is the situation very similar to how we did with controlled U and controlled V. Yes, because, okay, the first qubits just don't change. Yes. This intermediate qubit, yes, this ancilla qubit would not change because either both time it is executed or both time it is not executed. Okay? Yes, I just repeated the same scheme twice. Completely correct. Yes. But now it works independently of what was the value of qubit here. Yes. Because, so this one also doesn't change. And we need to check that, so if one of those things is not one, then here we didn't change any time. So either both time is executed or both time is not executed. If one of those is zero, then this one is never executed. So we need to consider the case when all here are equal to one. And if the input is zero, then here it is executed and here it would not be executed. If the value was one, it would be executed. So the idea is the following. So it calls uncompute, but in fact it just repeat the second time the same. And then it works independently on the thing. And now using this trick, combining with other ideas, we would be able to construct which one? So yes, in theory, it executes twice the same, but in the middle, so this one was changing what is happening here. Then in the end, it would be one. So then it would be not executed. Yes. And if it was one, then oppositely, the first part would not be executed, but then it would be executed the second. Yes, but here, this is important feature that I don't care what was the value of this qubit. And moreover, in the end, it would be the same. Yes, so this scheme acts the same as multiple control tensor identity. Yes, so this is the feature. So it's not necessarily be a clean qubit. It can be used in some other computations. We just, how to say, we sublend it, we take it, use it for our calculation and return back untouched. Yes, basically. So in that case, you can substitute here the qubit, which is a part of other calculation, your thing. Yes, so this kind of, it's until a qubit, but you don't need +1 qubit to your computer. Yes, you just sublend an qubit from other part of your algorithm and return. So the next class I will finish with this story, and we will together play with the true, okay, I think with a simulator of quantum computing. So we will draw schemes, we will execute them, we will see what is the typical output, and so on. Okay, so questions might be from Zoom. Okay. Yes. So I started with n and basically put here n half and n half. Yes, but at the same time I make a scheme longer. Yes, so that's exactly we need time. We will spend part of the time of the next lecture on understanding how much if we, how to say, here I started with 1, 2, 3, 4, 5, 6, 7, yes, and decomposed into 5 and 3, yes. And after this, I need to decompose 5 into the next story and 3 actually, yes, and so on, yes. And the question, what would be the length of this scheme? And just using this trick, we would be able to get the scheme of the length n squared, but we can actually have one more trick and then construct a scheme of length n of it. Do I answer to your question? Yes, for this, and moreover, it's not in a way that I need that it starts in 0, and in the end I potentially change it. I take it with arbitrary value, and I return it in the same state as it was. So it's until for our algorithm, kind of it's, we not add a requirement for the quantum computer, please have one more qubit. We just tell that, okay, we cannot do this just with all qubits of our quantum computer. Yes, we can take arbitrary value, which is 2 times smaller than number of qubits in quantum computer. Yeah, so if you have an algorithm which 50 qubits work, solve one problem, 50 qubits solve other problem, you can take this one from other parts, yes, of your stuff, and it would not damage it theoretically. Okay. Okay. Thanks.